Hi everyone, welcome to this lecture on machine learning. We'll be providing a little bit of an arch overview of what machine learning is. We'll look at how a typical machine learning problem is tackled. We have our data, we train a model, we evaluate the model, and in fact we're going to go into a little bit more detail on how exactly we're going to be evaluating models. We'll look at binary cross entropy and look a little bit more in detail on one particular model, which is logistic regression. Why logistic regression? Because it's a nonlinear model that is actually quite easily expandable to a multi-layer perceptron model in PyTorch, as we'll see in the next class. We'll look at different types of errors. When you're training your model, what kind of errors can occur? How can we fix them? One of the ways to fix them is regularization, which we'll also see in a little bit more detail. This week's lab on Friday, lab or tutorial, will be on PyTorch basics. So what are tensors? How can we use grad function? Grad function calculates partial derivatives or partials. We'll run simple models such as logistic regression and how do we evaluate, train these models, and how do we work with the GPU, not the CPU. Okay. But first, let's talk a little bit more about what machine learning is. There's a lot of buzzwords going around these days. We have artificial intelligence, machine learning, deep learning. What is what? Okay. Artificial intelligence, as you've seen, is more than just deep learning, neural networks for sure. And it's also more than trainable models that we see in machine learning. I think the proof is the last 4 weeks with Prof. Quan Hui, in which you saw some more classic AI, rule-based models, search-based models, etc. Okay. So within AI, we have a subsection of machine learning in which we basically learn our models from data automatically. Okay. And we can use many techniques for doing this, and I'm sure a lot of you are already familiar with some of these techniques. We have logistic regression, neural networks, KNN, reinforcement learning, etc. Now, a particular subset of machine learning algorithms is what we refer to as deep learning or deep neural networks. Okay, deep learning has been responsible for the latest AI boom from around 2006, as you remember from previous class. Okay. In machine learning, we usually parse a lot of data and then learn models from this data so that we can predict something that's going to happen in the world. Okay, so rather than hand coding rule-based models, we actually try to train the machine to automatically sort of predict what's going to happen without giving it rules. So machine learning, the idea actually comes from these early AI people that I talked about in the last class. But a lot of the advances have been made in recent years simply because now we have the computing power, we have the big data through the internet, increased storage capacity, and we have GPUs to process all this data. It should be worth mentioning, though, that machine learning currently typically focuses on very narrow tasks, and this general artificial intelligence or artificial general intelligence still is out of reach with most machine learning approaches. So let's look at some definitions of machine learning. Herbert Simon says that learning is any process by which a machine improves performance from experience. Tom Mitchell uses a definition that says machine learning is the study of algorithms that improve their performance P at some task T with experience E. Okay, so any well-defined learning task is given by T PE, okay, the triplet. We'll be coming back to this definition in a little bit. So when is machine learning used? Well, machine learning is used when human experience does not exist. How do we let a rover navigate on Mars? We don't know. It also is used when humans can't explain their expertise. Okay, so for instance, when I was creating a music generation algorithm, I could perfectly use rules when I was generating music such as counterpoint, which is a type of Renaissance music that inspired Bach, for instance, that has very specific rules. But if you're looking at pop, metal, or rock music, we don't have the specific rules, so we need to use machine learning and learn by example. Okay. Maybe we're dealing with customized models. Think of personalized medicine. Or maybe some models just are based on a lot of data. Think about gene detection models. We don't have rules for that. It's just a lot of data and we're trying to learn patterns. Okay. So while machine learning is great, it should come with a disclaimer because machine learning isn't always right. Okay. There could be no need to learn how to calculate payroll, for instance. What if we have an automated vehicle and it needs to learn that a stop sign, it needs to stop? Okay, you could give it 1,000 examples of a car stopping when there's a stop sign in its vision. Maybe you can just say, you detect stop sign, you stop. Okay. So typically machine learning has 3 components. First, we deal with our representation. What is our data? Then we optimize a model to fit this data, and then we evaluate the model. Okay. From experience, a lot of the tweaking and coding is put into the first component, the representation. So what are a few tasks and techniques that we find in the field of machine learning? Typically, and the most famous ones I would say are classification and regression tasks. Classification, we would like to classify which one out of a discrete number of classes a sample belongs in. Okay. You have images. Is this a cat or a dog? That's binary classification. You might have a set of images and you want to say, does the image contain a ball, a dog, a cat, or a sofa? That would be multi-class classification. There's a myriad of techniques that we can use for classification. Like some of the simplest, decision tree, naive Bayes, logistic regression, support vector machine, quite powerful model that does need some optimization. Neural networks and ensemble methods, which are methods that actually combine different methods together. This is a very interesting field and typically offer very powerful predictive models. Think of ensemble method. There are different kinds of ensemble methods, but in the simplest case, let's say I make a prediction with logistic regression, SVM, and decision tree. Maybe I take those 3 predictions and I learn a new model from these predictions that gives the actual prediction. So you leverage the strengths of different models in an ensemble method. Okay. Second type of task, a regression task, is when you're trying to predict a number. Linear regression, again, support vector regression. Neural networks can handle this as well. Okay. Then we're coming into the unsupervised methods, for instance, clustering. I'm sure you've all seen this in your statistics class. We can use k-means or hierarchical clustering to sort of find examples of instances that belong together or have similar properties without them having a label. We have association rules, which is very common in data mining. For instance, association rules can find that in the sales data of a supermarket, a customer buys onions and potatoes together, while they also like to buy hamburger meat. Okay. That would be an example of an association rule. In this case, it would be onions and potatoes, then also they will buy hamburgers. Reinforcement learning. Also a very powerful technique. I won't talk too much about this because the last 4 weeks of this class will go into much more detail on this. Okay. Now, we have different tasks. We can also look at the types of learning. Okay. So traditionally, we have supervised learning or inductive learning. So you get training data and you have your labels and you learn to predict the label for unseen data. You have cat and dog images together with a label that says cat or dog. You input it in the machine, in the model, and you get a prediction. It becomes more challenging if you do unsupervised learning. With unsupervised learning, you only have your training data without any desired label. So an example of unsupervised learning would be clustering, whereby you just look at your data and then you predict which samples belong together, and then you can draw conclusions from that. Now it gets interesting when we look at some recent developments, for instance, semi-supervised learning. Basically, in semi-supervised learning, you have a small set of labeled data, so you do inductive learning, and then you also have a large set of unlabeled data. So you'll use transductive learning to sort of transfer what you've learned on a small set of labels to the large set of unlabeled data. Okay. For instance, think of an exam. You have some sample questions and answers, but now you need to do transductive learning and sort of predict what new answers to new questions could be. Related, but still a little bit different, is self-supervised learning. Okay, this is a subset of unsupervised learning, and it's often used for feature learning. Okay. In self-supervised learning, you use a pretext task. Okay. It's a task that we've invented, we're not interested in. For instance, you have images. Maybe you will rotate the images and try to predict if the image is rotated or not. So you have unlimited labels for that because you're creating the task. But why are you doing this task? Not to see if you can actually predict if they're rotated, but you're interested in the learned latent features of the model. So then you can use these features for a task for which you don't have so much data. Okay. So some people say, I found this quote here, that the AI revolution will not be supervised. Okay. The future of a lot of advances in the field are in the semi and self-supervised learning, because not all tasks, not all tasks have labeled data available. Okay. I work in the field of music myself, and we constantly struggle to find labeled data. Like, an important problem is audio transcription. Now, we do not have a lot of MIDI files that are perfectly aligned with audio files. Do you have the exact sheet music of where notes are in the popular pop songs that come out? No, we don't. So labels are scarce, and the future for sure is in these unsupervised semi or self-supervised learning technologies. Okay. Now let's get back to this definition of machine learning that we saw earlier. What does a machine learning system consist of? Okay, we always have a task T. Let's take an example. We want the model to learn how to play checkers. We have a performance measure P, which would be in this case the number of games that the model wins. Training experience would be a set of games played against itself. So this would be our training data set. Now, once we have this, we need to define or choose what exactly it is that we're learning. So our target function. The target function in this case is what kind of output do we expect from the system? We need to know the next move given the previous set of moves or the board states. So we represent the target function using a model, and that could be expressed, for instance, as a linear combination of all its inputs. In this case, the inputs could be the number of black pieces on the board, the number of red pieces on the board, number of black kings, number of red kings, etc. So once you have all these xi's, the inputs, you can form a linear combination to predict the next move, which in this case would just be a linear regression. Then we choose a learning algorithm to infer the target. This means to optimize the coefficients of our linear model so that the prediction is as good as possible. So I want to look at how do we evaluate these machine learning models. If we're looking at classification methods, we typically look at accuracy. Okay. I often see this inaccuracy in my students when we have, let's say, a multi-class problem or even a binary class problem. They show me an accuracy of, say, 90%. my first question will always be, how balanced is your data set? Okay. Let's say I'm predicting hit songs. My data set has 90% non-hits and 10% hit songs. Student comes to me and they say, my model has 90% accuracy. To me, that means nothing, okay? Because what if you predict that the song is always a hit? Wait, sorry. What if we predict that the song is always a non-hit? I put it the other way around. In this case, we predict always non-hits, and in our data set, we only have 10% hits. That means the model will have 90% accuracy. But it is a baseline, naive, bad model. Okay. So we always need to look at the class-specific accuracy. In this case, if we predict always non-hit, then our class accuracy of non-hits would be 100%, and the accuracy for the class of hit songs would be 0%, so really bad. Okay. So something to keep in mind, this is very important. That's why there are other metrics that you can use. I like looking at confusion matrices because it gives you an even better view of what you're misclassifying exactly. You see a confusion matrix here at the bottom left. We have true positives, true negatives, false negatives, and true negatives. Okay. Basically, if you fill in this matrix, what you want is you want high values on the diagonal that goes top left to bottom right. Okay. The true positives and the true negatives, that is what you want to optimize. Now, looking at this kind of matrix is actually very interesting because it would allow you to spot if there's a specific class for which you're performing badly. And in that case, you can have a look at your data set and see what kind of things you can improve. Maybe you're missing some features to improve this result. Okay. Related to this, we can get precision and recall, and F1, of course. Precision, also called positive predictive value, is a fraction of relevant instances among the retrieved instances. Okay? And recall, also known as sensitivity, is a fraction of the total amount of relevant instances that were actually retrieved. Okay? I think the best way to look at it is in the graph that I put on the right, which is from Wikipedia. I forgot to mention the source, for precision and recall. Now again, because you have two metrics which can be annoying to optimize, these are often combined in the F1 score, which gives you the harmonic mean of precision and recall. Okay. Other metrics include the receiver operating curve, or ROC curve. It is drawn on the right, and for an ROC curve, it plots the true positive rate against the false positive rate. For random predictions, we would have the diagonal, the blue diagonal, and a model that performs very well would be sort of bent to the top left as much as possible. Okay. If you're wondering how the curve is made, it's actually by varying the prediction threshold. If you have a binary model, usually you'll have a probability for each of the classes. And typically you could say the threshold or the cutoff is sort of 50%. Like if you predict something to be in class 1 versus class 2 with 51%, it will be in class 1. But you can vary that threshold because sometimes it's actually better to vary it. So that's how they make this curve. A very related and I think a very powerful metric is the area under the curve. It sort of says it. It's the integral of the receiver operating curve. And it gives you a value that's very much related to accuracy, but takes this class imbalance into account. Okay. So this is for classification problems. If we look at regression problems, a very typically used metric is the mean squared error, or sort of the L2 loss. Mean square error just gives you the difference between the actual and the predicted values squared and averaged. Okay. Very intuitive. If you're interested in different types of regression laws, like the absolute square, absolute error, etc., there's a very interesting blog post that I can refer you to. But for now, we won't go into much more detail. What about the difference between two probability distributions? Okay, because in the end, our model outputs probability distributions. So in order to fully understand this, let's have a look at information in the field of information theory and how that is defined. There's a very famous mathematician, Claude Shannon, who wrote a paper called The Mathematical Theory of Communication. And that was sort of the origins of what we call the field of information theory. Information is generally measured in bits. Okay. And very loosely, you can say it's the amount of surprise that's arising from an event E. Okay. So it's defined as a negative log probability. Okay. Let's take an example. There's only 3 girl names in the world. Doreen, very nice name. Skylar, which happens to be my daughter's name, and Annabelle. Very common. Annabelle occurs 79% of cases, Doreen 20%. It's popular in the Netherlands. And Skylar, very rare. Now, how much is the information entailed in the name Skylar? So we take the negative log probability of the occurrence probability, and that would be 6.6. So a very high surprise. Now, if we look at Annabelle, which is a very common name, the negative log probability is 0.79, so a very low surprise or low information entailed in that occurrence or that name. Now, note that we said that it's measured in bits, so that means we can actually read this as the information entailed in Skylar is 6.6 bits. If we were to use not the logarithm of 2, but the logarithm of e or ln, then the unit is actually called nats, N-A-T-S. So sometimes, in some cases, they use the logarithm of e. In that case, the value changes, but it's because the unit changes to nats instead of bits. This is just FYI. Now, related to information, we have the concept of entropy. Entropy is the average level of information inherent in the variables' possible outcomes. Okay. So we just average it, basically. Okay. Let's take a look at the names distribution. We have, in the previous slide, I think the occurrence was 20%, 1%, and 79%. So if we fill in the formula above, it gives us that the resulting entropy is 0.26 bits. Okay. It's low entropy. Okay. That makes sense because most of the names are Annabelle. So in 79% of the time, you're certain what the name would be. And only in that's not how it works. Only in a few percent of cases, you're surprised, meaning that if we calculate the entropy, it's very low. So, taking these concepts, we can now define the difference between two probability distributions P and Q. And we can calculate that under the name of KL, Kullak-Leibler divergence, or relative entropy. KL divergence measures an expression of surprise. So if the probability distributions are close, it would be surprising if it turns out that they're not. So then the KL divergence will be high, if not reversed. Now, how do we derive the KL divergence? We start from likelihood ratio. The likelihood ratio basically tells us how much more likely a sample X has come from distribution P than of distribution Q. We just divide the probability of distribution P divided by the one of distribution Q. Okay, quite easy. Now, if you have a lot of independent samples and you want to estimate the likelihood function taking into account all these samples, then you need to just multiply all these probabilities. Okay. Now, we can take some logarithm rules. If we take the logarithm of a multiplication, it turns into a sum. So that's how we arrive at the equation below. Take the logarithm, so the product turns into a sum. So how much now, on average, does each sample gives evidence of distribution P rather than Q? So for this, we take the expected value of the likelihood, and we arrive at the equation below. The difference with the previous slide, is that we take the average. Okay. So what term do we add? We add Pxi, which gives us the probability or the number of times that xi appears, and it helps us to take the average. Okay. It lets us take the average of the likelihood. So we can rewrite this a little bit using the log rules again. Maybe useful for you to freshen up on these logarithmic rules if you don't. And we change the division into subtraction. Okay. That is the definition of the KL divergence. Okay. Now, as it turns out, the first term is actually the entropy, sort of the information content of distribution P. Subtracted from this is the information content of distribution Q weighted by P. Okay. Interestingly, that means that if P is a true distribution, then the KL divergence is the amount of information lost when expressing it via Q. And hence it gives us a measure of calculating the distance between two distributions. Now, a related concept, cross-entropy. This is at its core a way of measuring the distance between two probabilities P and Q. So it offers us a second way of measuring this. So entropy on its own, it's really just a measure of a single probability distribution and how much surprise is in the distribution. Cross-entropy, or CE, is a combination of the entropy of the true distribution P and the KL divergence between P and Q. Okay. So using the definition of the entropy and the KL diversion, we can actually fill in the formula above and arrive at the below formula for cross-entropy. This is a formula that you'll actually come across quite a lot in machine learning. Now, interestingly, cross-entropy is minimized when we're trying to learn the model because we really want to minimize the amount of randomness and surprise in the model. Right? The model should know everything. Okay. Let's take an example here. We are trying to predict the one-hot vector. There's a bunch of entries, and there's only a 1 in index position 2. We start from index position 0, 0, 1, 2. The output layer of our model here is a softmax. Now, I will go into detail about softmax and sigmoids a little bit later. Softmax basically is a normalized exponential function that takes a vector of real numbers and it normalizes it into a probability distribution consisting of, in this case, 10 probabilities proportional to the exponentials of the input numbers. Okay, what does it mean? It's a multi-class classification tool that gives us probabilities for each of the 10 classes here, and the sum of all the probabilities is 1. In binary classification, we use sigmoids. In multi-class classification, softmax will do the trick for us. Okay. This aside, our output of our softmax last layer of our model is 0.01, 0.02, 0.75, etc. To get the actual predicted class, we take the class with the highest predicted probability, which is 0.75. So in coding terms, you take argmax, you take the maximum. You take the index position of the maximum element, which is 2. So for all values apart from 2, we actually saw that in the real probability distribution, they occur 0 times, so it's 0. So that means if we look at the cross entropy formula from above, it actually collapses to minus log of 0.75. Okay. So it's easy to calculate. This would be the cross entropy of our example. Okay, there's a difference between cross entropy and KL diversion. Both measure the distance between probability distributions, but they do it in a slightly different way. So cross entropy measures the average number of total bits needed to encode data coming from a source with a distribution when we use model Q, and KL diversion is the average number of extra bits needed to encode the data. Okay, so slight difference between how they're calculated, but they work towards the same goal. Now let's have a look at logistic regression. In logistic regression, our classification goal is binary. So we're given an input space X. Our goal is to predict for every sample X belonging to the input space X, which class it belongs to. So for two-class classification, the goal is to predict in the output space, which goes from -1 to +1, or as you'll later see, sometimes we normalize to 0 and 1, which one it is. Okay. We can generalize this to multi-class classification, whereby we have C classes, but here first let's focus on two classes. Okay. Now this does mean that we're sort of unsure of all fx that are around 0. The larger the absolute value of fx, the more confident we are that we're predicting the right class label. Okay. If fx is really large positive, we're very confident to predict class +1. If fx is very small, sorry, this should be large negative, we are very confident about prediction -1. Okay. Now, how can we encode this as a probability? So we need to map the output of fx, which goes from -infinity to +infinity, to 0, 1, such that 0 gets mapped to 0.5. Okay. +infinity is mapped in the limit to 1, and -infinity is mapped in the limit to 0. Okay. It's important that I actually mention that 0 should be mapped to 0.5 so that the prediction accuracy, or sorry, the sort of the neutral zone in the predictions, that where we're not sure about, should still be in the middle between the prediction 0, 1. Okay. Now we can actually achieve this by using a sigmoid function. Okay, the sigmoid function is the SA, which is e to the power of a divided by 1 plus e to the power of a. Okay, we can slightly rewrite this formula by pulling aside e to the power of a, and it results in a very popular notation, which is 1 divided by e to the power of -a plus 1. I'm sorry, if I'll be teaching this on a whiteboard, I'd be doing the math with you, but it's just easier to show you. So now let's look at the limit. If a goes to -infinity, what happens? Okay, e to the power of -infinity, you know, any number to an infinitely small power is 0. Okay, so in this case, the result is just 0. Great, that's what we wanted. If we make a go to the limit of +infinity, it's easier if we start from not from this first equation, but it's easier if we use the rewritten form. In this case, again, we have a to the power of -infinity plus 1, which just result in 1. Perfect, this is what we wanted. Okay. So this logistic sigmoid function, I've written the first line of the previous slide again here for you, is very useful and is the core of the logistic regression. Okay. So we should note that for multi-class classification, we don't use a sigmoid activation function. We use softmax, which is a variant. I mentioned softmax a few slides back. Okay. The formula for softmax looks like this. E to the power of some function divided by the sum of e to the power of that function. Okay. For all classes, the sum over all classes. All right, so we're sticking to logistic sigmoid for now, and if we plot the logistic sigmoid function, we see something like this. Here we varied, we added a term c in front of a, so that we can see what the influence is of increasing a by a factor of c. Okay. We see again that around the 0 point, our prediction is 0.5, so we wouldn't be sure which class to predict. The further away from 0 we go, the more certain we are about which class we predict. Okay. Right. So in the logistic regression model, we just have a linear combination of features plus a bias, wx plus b, and we plug that into the a in the previous formula. So we take the sigmoid of a linear combination of features. That's all the logistic regression model is. So the resulting formula, this is the form I'm most used to seeing it, is 1 over x to the power of this long equation for each feature, because x is a vector here, a vector of all input features, plus w weights that you learn, coefficients that you learn, minus a constant also that you learn, plus 1. The output of this model will refer to as h of x, and it is between 0 and 1, so perfect for probabilities. Again, usually our class cutoff would be 0.5, or threshold would be 0.5 to classify the output between two of the classes, but we can vary our threshold in some cases. Now, if we're training this model, we can make use of the cross entropy. How do we do that? So suppose we have a sample xi. So suppose we have for every sample xi a function p xi, which provides a probability that tells us that it either belongs to class +1 or class -1. Okay. We need to map this 0, 1 probability that we had earlier to -1 and +1 class labels. So in order to use this, we need to do a small mapping function. Okay. So I call it I hat I, would be the mapping of the 0.5 output to the -1 +1 output. So, sorry, a mapping of the 0, 1 output to -1 +1. Okay. Okay, now let the cross entropy loss for a sample xi is all the input features, yi is the class, be given as follows. So if the class is +1, the cross entropy is minus log of the probability of x. Okay. If the class is -1, it's minus logarithm of the p2 of x1. All right, p2 is the second probability. Remember here that we have a function p which gives us the probability of belonging to class 1 and the probability of belonging to class 2. Okay? So, in this case, the cross entropy combines these two and results in this formula of the cross entropy loss for logarithmic binary regression. Okay. If you're wondering how we're getting from this to there, we plugged it into the formula for logistic regression, which I put here again. And then in the second term, what we did is we actually plugged in P1 where P2 occurred. So why can we say this? Because we have two classes. If my P1, I predict that X1 is going to belong to class P1 with 30%, that means automatically that P2 is going to be 70%. Okay. P1 plus P2 need to be 1. The total probability needs to be 100 over all the classes. So knowing this, we can substitute P2 by P1, 1 minus P1 would be P2. So this is exactly where P2 would be. That's where we replaced it. Okay. All right. So in essence, we see, if we look at the output of the logistic regression model, H, we see that the probability of belonging to class 0 goes up, and the probability of belonging to class 1 can go down, depending, on the output of the logistic regression. This is how we'll probably usually, so there's a cutoff at 0.5, which will determine if our output belongs to class 1 or class 2. And at any given point, the sum of these two curves, if you were to sort of take, okay, let's say H is 0.3 here, if you would sum this y value with 0.3 y value here, it would total to 1. Okay, so we can look not just at one sample, because in the previous slide we looked at one xi, one sample, one data value. We actually need to look at the loss between the two distributions. Okay, at the real distribution and the predicted distribution. So how do we look at the loss between two distributions? We need to average this overall occurrences. Let's look again at this. We start from this equation, right? The loss, cross-entropy loss. And we plug in our model for H. Our model, if you remember, is the sigmoid function of this linear regression. Okay, so this means that the optimization problem to be solved is just this cross-entropy loss with this plugged in. What do we do with this loss? Remember that entropy is a measure of surprise and chaos, so it means that we need to find the lowest value. And we need to find not just the lowest value, but it says argmin here. That means that whatever class has the lowest value, that is the class that will classify it to. Okay. Now, whenever we're optimizing, we want our cost function to be convex so that we can use optimization functions. Okay, this is so that we could reach the global optimum here and not get trapped in a local optimum like displayed here. Okay. All right, so we can do this. We can use optimization functions such as a gradient descent. This is not a course on optimization, so I'm just very briefly touching this, but we will look into gradient descent as it's such a prominent algorithm in machine learning. How does gradient descent work? Well, first, whenever we have a model, it has weights, coefficients that we need to learn. We initialize the weights randomly using a normal distribution. There's other ways to initialize the weights, but we won't go into this. Then we compute the gradient. The gradient is basically the partial derivative for each weight. We update the coefficients using the formula displayed here. Oh, here we go. This is the formula we use to update the coefficients in gradient descent. You notice that there's an alpha, which is the learning rate, which is a parameter we set. And the alpha, so basically from the current weight, we subtract the learning rate times the gradient. Okay. And then that gives us the new weights. So in gradient descent, we start from a super simple cost function. Sorry, not cost function. We start from a super simple function, x plus y. And we set the initial value x is 2 and y is 6. The output of this function obviously is 8. Now the question here is, how do we tweak the values of the inputs to decrease the output? Okay, so how do we optimize the coefficients? Let us start by differentiating. Sorry, how do we tweak not the coefficients here, but here is the input. It's a simplified example. Let's calculate the gradients first. Gradients are the partial derivatives. Simply because this is such a simple function, the partial derivative for both x and y is both 1. That means that the gradient is 1. We fill this in the formula that we saw before, and we see that these derivatives can be thought of as the force of change on each input. Okay, so it's the change in every direction, x or y. So our new x would be the old x minus the learning rate times the gradient. Okay, learning rate is often put really slow, but there are strategies to actually dynamically change the learning rates, as we'll see in the next class. The gradient for logistic regression, let's see if we can calculate this. We start from the objective function, so fx, sorry, this is not fx, this is the cross entropy of fx, which I took straight from a few slides back. We remember that we have our fx here, which we call hx, which is the output of a sigmoid function. When we try to do the gradient with regards to w, so all of the coefficients, we get the following formula. Now, if you're unfamiliar about how to get from here to the calculated partial derivative for x, so for w, then I recommend that you look into your mathematics your mathematics course a little bit more into detail and refresh your memory. We just calculate a simple partial derivative to get this, and this is our gradient. Now we can just fill in the values and we obtain an actual value at each learning step. Here, this gradient that we came to has actually a very nice interpretation. It's the sum of the data points xi weighted by the differences between the predicted value and the true value. As you can see, we have the predicted value and the true value, which are weighted by xi. Okay. It's very nice. Okay. All right, so to just sum up binary cross entropy, our outputs of our model are in the range of 0, 1, which we can directly use as a probability for class label. The logistic regression is a linear mapping with the logistic sigmoid function on top of it. And it's actually a very nice model to move on to a single layer neural network. As we'll see in the lab, we're actually going to use sort of like a neural network in PyTorch to calculate a logistic regression model. It uses a cross entropy loss, which can be derived by using maximum likelihood on top of the probabilities for predicted class. Okay. Now, if we move on to multi-class logistic regression, what is typically done is, if we have 3 classes, we build 3 models, each for separating 2 classes. Okay. All right, now let's have a look at the things that we need to think about when we're training